Now let's try to understand what is computing. So as a first step, I'm going to go to the Wikipedia page of computing. So this is the wiki page for the computing. It is giving the typical textbook explanation for what is computing and a lot of such jargons. Definitely you can take your time and go through it. It's definitely useful. But we need something better, more fundamental. In fact, nothing to do with computers at all or machines in general. So let me ask you this question. So when you think about computing, what you really mean to you, being a student, what you might have heard the word computing, right? So let me take some input from you before I go forward.
Some calculations.
Okay. Calculations, good example. Yes. All right. Anything else comes into your mind?
No, as of now.
All right, cool. So calculation. So that's a good example of calculation. That's exactly what we're gonna take as an example. So how do we know that 1 + 1 = 2? Ever thought about it? No. Okay. So basically this kind of things are called axioms. They are basic rules. So they don't have any proof. They are basic rules which doesn't need any proof. Sometimes it's called hypotheses. Sometimes it's called axioms. I mean, it's all similar things. Basically, people take it for granted from rest of the experiments and stuff like that. Let's consider the example of these two numbers, adding these two numbers. So let's go to our whiteboard and let's add two numbers and see how it works. Okay. So let's see the number 1, 2, 3 and 6, 7, 8. Okay. So these are the two numbers we are planning to add. This is a big two numbers you are going to add. But what are you going to do? Tell me. So what are you going to do? You're going to add 8 and 3 first. Okay. 8 and 3. 8 plus 3 is 11. You're going to have 1. And why I put 1 instead of 11? Because you need to separate the carry, right? So the carry has to be separate. First we did an operation. So 8 plus 3 equal to 11. That's an operation. How did you know this? That is part of a table, the addition table we studied. In fact, it boils down to 1 + 1 = 2. It's like an axiom. We don't question that, this particular statement. We know that it's an additional table. So this is an operation. I'm going to put it O. And next is, you're not going to take the entire output of that operation. So if that operation, if, the word if is very important here. If it is greater than 9, if you're going to take the last one digit instead of the entire number. Okay. So in this case, it was greater than 9. So you took 1 instead of 11. This is a check we are doing. What we are checking? Checking if the number is greater than 9. So that is a check we are doing. And based on the output, we are taking two different decisions. Check and decision making. So if. Okay. So first is an operation. Second operation, or the second action we have done, is a check. And based on that, we took two different routes. Now what we're going to do? We're going to add that one here. Yeah. And we're gonna keep going, right? Again, keep going. What we are doing? We are just repeating. Yeah? Repeat the same thing. So adding a big number is nothing but boiling down to tables like this. So let me take a different color. Boiling down to tables. So these are the tables, lookup tables. I'm gonna call it lookup tables. So this lookup table or the axioms are your fundamental operations. You don't need any proof. And then what we're gonna do? We're gonna do some checks and pretty much repeat the process. Yeah. You take any computation, any action. That's what we're gonna see a couple more examples like this. This is how computation is done. Computation is all about breaking big problems into smaller chunks like this and repeat the whole thing, at least the computation in our perspective. There are problems which are not in this category. I don't want to discuss that part of the theory of computation here. So the problems which we're going to discuss for sake of our discussion, it's going to be problems like this. I'll give you an example of a couple of other problems which cannot be solved like this as well. That's totally different. So what we have here? So we have some operations and certain algorithm steps which we performed, certain checks we performed, and then we got the final result. Okay. So this example we have seen, and we have proved that it is nothing but breaking down into different smaller steps. Yeah, this is a pretty detailed step-by-step operation of what we just saw. Nothing new to it. We are going through different operations, and this is more detailed in the slide. I don't want to go in that depth, but if you want to check, you can go through this. So I'm gonna skip this. Pretty much same thing we saw in the whiteboard. So this is a different problem. Again, a similar problem, nothing fancy about it. Finding the smallest of 5 numbers. So we have 5 numbers. How are you going to find the smallest of these numbers? So what is the smallest in this 5 numbers?
2.
Okay, so how do you know that it's 2? Your answer is correct. How do you know? How did you think about it?
That's how we count.
Okay, so let's come into a step-by-step process again, just like before we did, right? So first you saw 2, you have 5 numbers, you saw 2. And you checked in your mind, whether 2 or 5 is bigger. You know that it's 2 is smaller than 5. Same operation you did for 3, and same operation you did for 8, and then for 3. So what did you do? You compared 2 numbers. How do you know that 2 is smaller than 5? Because you know that if you subtract 2 from 5, you will get 3, which is a positive integer. This is also boiling down to compare, then a move. If you think from a step-by-step perspective, it's all simple. It looks simple, but it may not be that simple if you have 1,000 different numbers. It may not be a simple problem. This is also a sample problem. Sorting this numbers, so we have 5 numbers, sorting this numbers in ascending order. If you split the algorithm like the way we did last time, this is also gonna look pretty similar. Do you want to try it out?
2.
Yeah.
3.
Yeah.
3.
Yeah.
5.
Yeah. 8. Yeah. How did you do that?
Compared, consecutive, change their place.
Change their place, exactly. Yeah. If the number is bigger, you moved it to the right. Yes. And if it is smaller, you moved it to the left. In fact, it is one of the most common sorting algorithms, which you just mentioned. Ultimately, compare and move. Sorting, as a matter of fact, is one of the most important operations computers does any day, just to give you a heads up. So again, problem is compare, move, simple operations. This is a search problem. The problem is finding at what position the number 8 is in this 5-digit. So it's a search operation. If the 8 is not there, we need to say that there is no 8. If there is 8, we need to tell that, in this case, the 4th place 8 is there. So we need to say that 4. Yeah. So that's the problem. It's a search problem. Again, same thing. You're gonna check if 2 equal to 8. No. You move further, and then next value 5, which is not equal to 8, coming to 3, which is not 8. Again, the 4th one, 8, it is equal to 8. You stop there. So that's what you're going to do. This is also very, very simple. So now let's see a complex example. I don't know how much the audience or you yourself used to this. So this is a fairly complicated problem. It is from mathematics called calculus. Evaluate an integral of 0 to 1 or 1 to 2 x log x dx. So I'm not going to explain any of this thing, but only thing I want you to understand is that if you knew how to do this, you will know that it is also exactly similar to what we just did. It all boils down to lookup table. First, we're going to find out the function, which is of integral of x log x dx. And then you're going to do some multiplication, addition, or subtraction, all kind of different operations, and you get to a particular value. This is all going into lookup tables, checks, some steps, some operations, simple things. There are different problems, rotation of a 3D object, playing chess, all these problems. These are very complicated problems. We saw simple problems in the beginning. All the problems like this. For example, right now, I'm helping someone who is writing a code in a programming language called Python. So he's working on something called genome sequencing. He was an ex-colleague of mine. And you know what his genome sequencing of COVID-19 strain? So it boils down to nothing but searching and sorting. It's a different kind of search and sort, but it's searching and sorting of different numbers at the end of the day. The problem boils down to that. So to summarize, so we have seen so many examples. All the problems we have seen boils down to simple calculations in the end. So any computing task or a problem can be broken down into simple steps, like we discussed. And a computer like the CPU we have seen can only do such simple things. It cannot do any complicated things. It doesn't know how to do DNA sequencing for any virus or anything. It doesn't know how to play chess. All it does is very simple operations, very fast and repetitively. We're going to see such operations pretty soon in chapter 3, but that's all it does. Very simple things, addition, moving, shifting, simple operations. And making a computer or a CPU does that is all about computer hardware. That's what computer hardware does. Computer hardware, the box we built, cannot do anything complicated. Now, it is a software or the computer program which is written by humans, or the algorithm, that is what making it do complicated things. Here, we're gonna build a circuit which adds two numbers using very simple basic operations. In short, CPU is not a smart worker. It is just a hard worker. So it doesn't do practically, any complicated actions. It just do simple things. So fundamentally, CPU or the chip we have seen is not a smart worker, but it's just a hard worker. One question here is, which is not addressed, is how small or how fundamental the operation can be. So I said basic operations, we have seen comparing, we have seen addition, so many things we have seen in the previous examples. So is that a fundamental operations? In fact, no. There are way more simple operations than that. We will see that shortly. For the purpose of this particular discussion, let's assume that it is addition, subtraction, multiplication, and compare or shift, etc. Not all the problems can be solved by the mechanism which I mentioned. Some problems needs more careful thoughts, which is not really part of our discussion. We are not going into the details of that. So this is a problem. I'm not going any detail into a problem like this, So here we have a problem, which if we give to a computing or an automated system, and to get the output, the correct answer with correct reasoning, it may need more than simple operations like we discussed. Not all the problems, but we are talking about problems which can be broken down into simple steps like we mentioned. So this is an example which cannot be solved using simple things like we mentioned. So this is not simple lookups and steps. There is more to it. There is a lot of problems like that. So these are standard problems while the time of this presentation which are not solved by any human being. Those kind of problems cannot be solved just putting it into a computer or any automation. So what is our limit? Our limit is algorithm. If you don't have the step by step, if you're not able to break your problem into simple steps, you cannot solve that problem using a computer or any other mechanism. Your steps are your limit. If you don't have the steps, you cannot solve the problem. For example, in the sorting problem we saw, if you don't know the steps to do it, you can't solve that problem. Simple, same thing. So no surprises there. So what is algorithm? Algorithm is nothing but breaking complex problem into very simple operation like we have seen. And a systematic, so that word here is very important, systematic. We need to have a systematic way to repeat what operations we've been doing to finish the entire problem. Remember the addition we did? In the addition we did, we just did the first number and rest of the number. It doesn't matter how many 100 number, 200 number, doesn't matter. We just repeated the same operation which we did on the first two numbers. So that kind of systematic repetition is needed. And if that cannot be done, the problem cannot be computed, like the previous problems we have seen. Yeah, this word is pretty important. Any questions so far? Okay, so these are again a sample of not typical problems we're going to discuss in this session or the scope of this chapter. Again, a normal compute task can be reduced to lookup tables, simple operations, a read, a write, add, subtract, shift, move, compare, etc. In fact, these are the main operations a CPU like the one we have seen is going to give you out of the box. Read, write, add, subtract, shift, move and compare. The last two ones, they are very critical. They does most of the job in most of the cases, surprisingly. And of course, repetition, systematic repetition. Systematic repetition and simple operations. That's a key of computing. So we have seen that complex problems are broken down into simple steps. Now, the question is how to implement these simple operations, how to create a device to achieve these simple operations.